Howdy, we're the GE Healthcare Scope team, and our project was increasing mobile X-ray efficacy through technology-assisted alignment. And don't worry, we'll explain what that means in just a second. But first, I am Matt, this is Jeff, Tuck, Jong, and G, and, well, this is us. Also, our Olin advisors were Sam Mahalka and Brad Minch, and our GE advisors were John Snyder, Tim Rose, and Hai Duong. And we just want to thank all of them because we couldn't have done it without them. Anyways, now to get started. Oh, whoops. GE, first off, General Electric, or GE, is a multinational conglomerate that does a lot of things, and GE Healthcare is the arm of GE that works in the health technology space. Specifically, they make medical, diagnostic, and imaging equipment, so things like X-ray machines, CT scanners, MRIs, stuff that doctors can use to see inside patients to help diagnose and treat them. Anyways, our project explores options to improve the mobile X-ray system workflow for GE's mobile X-ray systems by assisting in the alignment of the detector and the emitter. Now then, to explain what that means, well, in a hospital, there are fixed X-ray systems in radiography facilities, like sort of dedicated rooms, and then there are mobile systems. Now, ordinarily when a technologist takes an image for a radiologist to use, they prefer to use the fixed system. It has fewer moving parts, less things that can go wrong. But sometimes you have a patient who can't be moved to these fixed facilities, say someone in the emergency room or someone in the ICU. But these people still need X-rays taken, so the machine has to come to them. This is where mobile systems come in. In a mobile system, a free-moving emitter on like a wheeled base is brought to the room, and an X-ray detector, also free-moving, is positioned behind a patient in their bed. A technologist positions this detector, aims the emitter at the front of the patient, and then presses a button. A burst of radiation is sent out, which is then read by the detector, and that produces the ultimate X-ray image. Now, this works all well and good when the emitter and the detector are lined up properly, but if they aren't lined up, you start to run into issues. So, for example, this is a well-aligned X-ray. It has the ribs, the lungs, all those important things. But if the detector and the emitter aren't lined up properly, like say if the emitter misses or the detector isn't in the right place, you can get anatomy cutoff. This means that there's some important part of the image that is just not there. Or alternatively, if the detector is kind of slanted or skewed, you can get a distorted image, which also isn't all that useful. It gets things that are stretched out, magnified, or just plain lost. Now, whenever these things happen, there's not really a way to recover from it. You need to take an entirely new X-ray image. And this not only exposes patients to additional radiation, it also costs time for the technologists and just leaves patients feeling qualitatively worse about their overall X-ray and hospital experience. So that's where we come in. Now, GE came to us at the start of the year with the problem of how do we locate the detector behind a patient with respect to the emitter in front of them. And we can kind of break this down to a couple sub-problems. First off, if the detector is visible, say, behind an arm or around a shoulder, this is a pretty easy problem. Like, we can just see the detector and aim accordingly. The main issue comes, and most of the errors come, from when the detector is entirely obscured behind the patient. And in those cases, technologists just have to sort of remember where they put the detector or guess. It's not as good of a system at all. So this is where the errors are introduced, and this is what we were trying to solve. How do we locate something when we can't see it? So if we can figure out a way to locate the detector behind a patient without vision of it, then that will improve the X-ray experience and give GE a competitive advantage. So we began this year by exploring technologies solutions for localizing, methods for creating line of sight, or even ways to change the hospital room entirely so that we could see the detector from more positions. But before too long, after we had started reading technical papers, pulling up product spec sheets, we realized that we needed more information. So we realized we needed to go and actually see how these things worked in the real world. We needed to go into the field, which led us to Schenectady, New York, Ellis Medicine Center, a partner hospital that works with GE sometimes, and once there, we observed what the technologists were doing with the mobile X-rays in the field. We watched them, we shadowed them, we asked them questions, and once we were done, we had a much better idea of what the product or the problem space was that we were working in. So with renewed vigor after our site visit, we came up with a set of design criteria, things like cleanability and weight, to go along with, actually technically working, and use this to evaluate a variety of solutions. We explored things like bed sheets with RFID tags embedded in them, or ultrasonic localization, before ultimately settling on a solution that we believe a promising way to move forward. Specifically, using computer vision to get as close as possible to the detector, and then using short-range magnetic localization to close the gap.
Once we'd focused on this way forward, We decided to evaluate and prototype a couple of different versions of this set of technologies. So a few solutions to the non-line of sight localization problem have the issue where when obstructed by a human body, they can't really get to the localization. With magnetic localization, we can, but as you move farther away from the detector, signal strength drops off significantly. Other things like X-ray localization are just harmful to the patient. So our solution to this problem, like Matt said, was to get as close to the detector as possible with a line of sight method of localization, and get the rest of the way with magnetic localization. So you can see there's the X-ray source head on the left can see a fiducial marker on some kind of intermediary tag between the X-ray source and the detector that goes on the patient. And this tag also has an electromagnetic receiver on it that can tell us the signal strength of a signal transmitted by a transmitter on the detector. There's also an IMU on the detector to tell us more of the orientation of the detector. So this is an April tag. This is the fiducial that we were using for most of the year. This is what we've been playing with. It's a square, black and white, asymmetrical image that a computer can easily pick out. The computer can recognize distortions in this tag and the scaling of the tag to get full 3D pose information. As you can imagine, putting this on some kind of intermediary tag that goes on a person will give us half of what we need to get to the full alignment with the detector. We've been focusing on this and evaluating this for most of the semester, and we ended up developing a kind of a pure CV solution. While the technical crux of this problem lies in the non-line of sight solution to alignment, there are cases when sometimes the detector handle isn't quite as obscured, maybe a small corner and edge is peeking out. So we developed a system where you get the entire position of the detector from one of these tags. This is kind of a proof of concept right now. You get a full visual. As for the magnetic localization, we were able to evaluate the magnetics and see a correlation between the distance the magnetic receiver is away from the magnetic transmitter. This just means that given further testing and evaluation, we'll be able to get the full position of the magnetic receiver from the signal that we sense and sent back to the collimator. So once we add all of this back up, we get a full transform from the X-ray source to the detector. So where does that leave us? Well, we have a working CV solution with accuracy up to 1 centimeter, and we believe that the magnetic system is enough to get improve on for further testing. And we hope that GE uses this information to develop some kind of intermediary solution, kind of a middleman, to implement this further. We think this project has a lot of potential for improving hospitals and patients' lives, and we hope to see it used down the line. Thank you.